Welcome back. We are back once again. It is day 90 of Daily LeetCode. We have been stuck on a problem that shall not be named on this channel. It is called binary tree post-order traversal. We did the recursive version, but what we're stuck on is the iterative version, which I realize I'm struggling with now because my model of exactly how you would follow a tree through a call is actually a little ghetto. So I think I'm realizing now that my understanding or my mental model of how trees work, or following a call of a tree, following the call stack in a tree was a little messed up. I was just having a brain blast thinking of the problem. About 15 minutes ago, I was drawing it, and I think I might have figured out a solution within the paradigm of this code that we were writing. I think, actually, yeah, I'm already jumping into it. But legendary comments again by Thomas Wong. He says, try LC333. It's the ultimate tree question. We're going to have to try this one out. Hopefully it's an easy. I hope it's an easy. I am worried. I hope it's an easy because we are the LC Easy Extinction Committee. And yeah, Thomas mentions that we should work on DFS to conquer tree problems. And this is true. This is true. And I think, yeah, and he mentions, it's easy to translate your code into iterative solutions when you think of the call recursion as adding into the call stack. This is true. So I think what we're going to try and do, we're going to try our solution first, and then I'm going to try and marinate on. Thank you for the guidance. Thank you, great sensei. I will not let you down. We will solve this problem. So we're going to try the first version I just came up with, and then we're going to try another version by ruminating or marinating on Thomas's points here. But I think we might have figured it out. I think I might have figured it out. I think what we can do, right, is when a node has no right pointer, we could add it to the value array. I think is what I was going for. No, when a node has no right pointer, like when a node has no right pointer, then we add it to the value array because it would mean that we're done processing it. The problem that is confusing, however, given this tree here, when we have a tree that actually has a right pointer, when we pop back and enter it back at 2, we actually don't have, the child still exists. So I think the way to fix this is to actually break the tree. So this iterative traversal will break the tree, but I think it'll get us a solution that is iterative. So right now my key bindings are not working, which I'm just not sure why this keeps happening. Okay, now it's working again. So we're back once again, and I think we can do this. So I think, right, we're going to have one stack, right, and then we're going to pop it off the stack. Now, we were on the right track yesterday, I think, with r.push cur.val if, right, cur.right equals nil, right? And so what we really need to do is separate this into two logical sequences, right? If cur.right equals nil, then we want to do r.push cur.val. Otherwise, right, if it doesn't equal nil, it means that the child does exist. Since the child exists, what we'd like to do is actually, I think, push the current value back onto the stack, right? Or it might be easier if we save it. We'll say temp equals cur. All right, we'll see. We'll say stack.push cur. Right, and we also want to do, like we do down here, cur equals cur.right. I guess, yeah, there's a weird thing we have to do because we have to break the tree. We'll say temp equals cur, and then we'll say cur equals cur.right. But then we'll say cur.right equals nil. But now we can still follow, right, that tree and go down. And then we don't need this value portion. But I think this should work, hopefully. So let's just see, right? We're going to start root with 1, right? Our cur is going to be equal to root. Cur does not equal nil because it's equal to 1, right? Cur does not equal nil, so we're going to say cur equals cur dot left, right? But we're going to push 1 onto the stack. Now cur is equal to nil, and we have 1 on the stack. We're going to say cur equals stack dot pop, and we're going to be back at 1. We're going to say if cur dot right equals nil, it doesn't. So what we're going to do is push 1 back onto the stack. We're going to say temp equals cur. We're going to save 1, and then we're going to say temp dot right equals nil. Or we can just do something like this, actually. We'll just say next equals cur dot right, and then we can just do cur dot right equals, we'll just say next node equals cur dot right. Cur dot right equals nil, right? And then we'll say cur equals next node. But we can say we're going to push 1 onto the stack, and we're going to say the next node is going to be cur dot right, which is 2. Now cur dot right, the node itself, the value that we're pointing at, right? This arrow here, we're going to change it to nil, and we're going to say cur equals next node, right? Because it's going to be equal to 2. Right now we're going to be at 2, and the stack is going to have 1 in it, right? The cur isn't nil, and the stack has 1 element in it, right? So now we're going to see how we're going to start going left again. We're going to push 2 onto the stack, which is perfect. Wait, no. We're equals, yeah, we're going to be at 2, right? Yeah, so we're going to be at 2. We're going to push 2 onto the stack, which is perfect. Then we're going to do cur equals cur dot left, which is 3, right? Then we're going to push 3 onto the stack, right? Then we're going to be nil. Then we're going to do cur equals stack dot pop, which is now 3. If cur dot right equals nil, we're going to push cur dot val, which is 3, right? And then cur is and we can just say cur equals nil here. And then we're going to do cur equal to nil, right? But stack.length is not 0, so we're going to, go back into the loop. Cur is nil, so we're not going to do this part right here. Cur dot is going to equal to stack.pop. We're going to be at 2, right? And then we're going to say cur equals stack dot. Well, I'm getting confused. We're going to say cur is equal to stack.pop because the last value on the stack is going to be 2. Then if cur dot right equals nil, which it should, we're just going to push 2, cur equals nil, right? And then stack.length has 1 element in it, right? We're going to skip this because cur is equal to nil, cur equals stack.pop, which is 1, and cur dot right should be nil, so we're going to push 1. So I think this should work. So it works for this weird one. Let's try the example test cases. Oh my God. Oh, it's free. We're free. Oh my God. Oh my God. Oh my God. You can't beat that. That is amazing. That is amazing. This is why we do the grind. This is why we work at stuff, man. This moment right here is why we work at, like, these are the money shots. I can't believe iterative post order got me so bad. Now, I'm excited to read the solution because I think there's definitely a simpler way to do this, but just being able to finally see through the madness, oh man, I feel like I've definitely understand in order, pre-order, and post-order way better, and especially the mechanism by which we create that traversal, especially using this code block. Oh, yeah. I mean, the time complexity would be linear time with linear space in the stack. So, feels strong, man. Wow, I can't believe. And there's not even a solution for it. Well, I'm sure there's a solution in discussions or submissions. I'm just going to say iterative to see how they did it in iterative. They use the previous. So if node.write doesn't exist, or pre is equal to node.write, then you append the value stack.pop pre equals node. Node equals node.write. I definitely thought it would be a little. I thought it would be a bit more. And I think he just reverses the array. I guess I thought it would be a bit more elegant. So yeah, it's interesting. I thought about doing a 2-stack version, but I kept getting confused. Stack 2, and then stack 2, then you cur equals. Yeah, we should probably learn a version that doesn't break the tree, and I think that version is probably using previous. But yeah, wow. Okay. Feel strong, man. Oh man, yeah. The dopamine receptors in my brain are ticking at 1,000 times a second, but we're gonna continue to focus up. We have given two strings, S and T, determine if they are isomorphic. Two strings S and T are isomorphic if the characters in S can be replaced to get T. Interesting. All occurrences of a character must be replaced with another character while preserving the order of characters. All occurrences of a character must be replaced with another character while preserving the order of the characters. No two characters may map to the same character, but a character may map to itself. I don't really understand this. So we have an example 1, S is equal to egg, T is equal to add. Foo is equal to, S is equal to foo, and T is equal to bar. Okay, so it says two strings S and T are isomorphic if the characters in S can be replaced to get T. All occurrences of a character must be replaced with another character while preserving the order of the characters. No two characters may map to the same character, but a character may map to itself. It sounds like what they're saying is E, G, and G, right? We have E, which is a character, right? And G, which is two characters. Then we have A, which is a single character, and then D, which are the same two characters. It seems like what they'd like us to do is check that character. I guess what they'd like us to do is for every pair of two characters, check that it's not the same as its previous character in both strings. So given S and T, right, we have E, right, and the character before E is nil. We have A, the character before A is also nil, right, which would mean that they both have the same outcome, right? Both of them are not equal to their previous characters. Then we have G, that seems to be the same here with D and A. And then we have the second G here, so G is the same as this G, which would mean that this would have to be mirrored here. I feel like this is true because if you take that idea and you bring it to example 2, right, F, the character before F is nil, same for with bar, but O and F are separate characters, right? And then R and A are separate characters, but O and O are the same character. And that creates a mismatch or an asymmetry. But in this one, it's particularly true. We have P and P, which are the same. All right, and then we have 3 separate characters. So I guess we have to, what we said about 2 characters being the same doesn't quite make sense, just because in this case with paper, we can't exactly guarantee that the mappings match, right? That P matches to P and T matches to T. I think what we really want to check, characters have the same mapping. Characters of both strings have the same mapping, I think is what they're asking us to check. They're saying all occurrences of a character must be replaced with another character while preserving the order of the characters. No 2 characters may map to the same character. So I think, what if we used we created a hash Right. So what if we created a hash for both strings, and the goal here would be that the key of the hash would be the index, right? Key is equal to index, value is equal to string of mappings, right? So for a given, so if we had something like, for the string s, which is egg, right, we'd have something like this, right? S's map would look something like this, where 0, which is the first indice, right, 0 maps to index a string, right, of 0. And G, right, maps to the index or the string 1, 2. And then we could do the same for T, right? And we'd actually get the same map or the same hash, basically, which would be the goal. Right? Because D would map to indexes 1 and 2 as well. So then the goal would just be to afterwards compare hashes. And I think you could just do that by concatenating all the strings, basically, and just checking if the strings were equal in the hash. Compare hashes by aggregating values into strings. And so I think this could work. So maybe we'll do, we'll try that and see if that's what they're looking for. We can create a function called create hash, it'll pass it a string, and it's going to return a hash. We'll say hash is equal to hash dot new, and the default value is going to be an empty string. And then we can say for each, we can't actually, well, you can't actually do that for strings. We'll just say we want to iterate over all the indexes in a string. And we'll say, so how would we create that mapping? Well, this current algorithm would actually be pretty slow, but we actually don't even know if it works. So we'll see if it works first and then optimize it. But for the hash, we'd have an index, and the only way we would know what other character matches this is if we did car equals string sub idx so it'd pretty much be squared time for the each string. We'll say inner index we'll just say outer car is equal to s sub idx, and then we'll say if outer car, we can actually have an inner car is equal to s sub inner idx. It equals inner car and idx does not equal inner idx. Then what we'd like to do, we'd like to say hash sub idx plus equal inner idx. And then we could return the hash, and then we could say s hash equals create hash for s, and then we'll just put s hash to start, and then we'll just return true to start. But let's just see, we iterate over the string's length, each do idx, we have an outer car, and then we iterate over the string again where the indexes aren't the same. We say inner car equals s sub inner idx, and then if outer car equals inner car and the indexes aren't the same, then for this index we're going to add, right, for 0 we're going to add the indexes that it maps to. With the variable we created was called string. Let's just call it s. So I'm pretty sure that's what we used everywhere. This is conversion of string. So we'll just say dot to s. And maybe we could actually say it's okay to map to yourself. So that looks fine to me. And then we can do something like t hash. And then if we put s hash and t hash, we should get the same thing. Now that I'm thinking about it a bit more, I wonder if instead of the hash in itself, we'll just say it creates an ID, which already, so just so we don't have to iterate over the hash again, what if we just did ID plus equal IDX, right? And inner IDX, instead of returning hash, we return ID. Then we could just check if the strings were the same. And so maybe we could just do return equals t hash. Let's try the example test cases. Seems to work. So it looks like this is what we're supposed to be checking. Now we know that this n squared is just a little too slow, which is actually fine. Because we don't have to do this n squared. We don't have to do this n squared operation. What we could do is first, because we know we can just compare the strings, we'll keep that, and then we'll copy this first iteration, and we'll actually create a hash that we'll actually use, and this is a little confusing, but maybe we'll just call it car hash equals hash.new, and the default value is also just going to be a string. And we'll just say car is equal to s sub idx. And then we'll say if car hash dot exists car, like if this character exists in the hash, then we want to add car hash sub car plus equal the index that we're at to a string. Now I'm realizing I think what we're just, this is the same thing. So I was writing this function to optimize this one, so we could do a linear time and build linear time iteration to build the hash of characters to indices. But I think if we just put car hash, I think we end up with something very similar. We still need, I wanted to test something. We still need hash.new. Why is my car hash empty? I don't understand. Just wanted to see, but let me just think this through. Car hash sub car plus equals idx2 string. Yeah, it'll always be empty. I think what we just want to do is car hash sub car plus equal idx dot 2s. And then our expected value would be e maps to 0, and then g, right, maps to 1, and then we get g again, which also maps to 2. So what if we just do an add to start? Yeah, so we end up with the same thing. Now I'm not even certain you have to do this whole thing, or that you even need car hash. I think what we just want to know is that the pairs match. We do need car. No. I don't think we need car hash. I think we could just encode this as a string. We just want the strings to be the same. We'll say 0, 1, 2. So you could just say ID plus equals idx.toS. And we could put ID. Right, no, yeah, this one is just adding the numbers up. This one's not the same. What am I doing? This would just be adding the numbers. Yeah, I'm just counting the characters in the string at this point. Yeah, I think you do need the character hash. Right, and you also need, I see, yeah, you also need to, yeah, you basically also need to encode the index of the character as well as the occurrences. So we see here with foobar, right, we have FO, right? Ultimately, the string is the same, 0, 1, 2, 0, 1, 2. The problem is 0 maps to 0 and 1 maps to 1, 2. So the actual ID here is incorrect. I think what we're looking for is something like car hash dot each do kv, and then we do ID plus equals, and we don't really even want yeah, we might just have to iterate over the string again, because doing over the hash, we don't get the indices, or I don't know how to do that in Ruby. So instead of this, we would just say ID plus equals index, right? And then you can also just insert car hash sub index as well, and then return ID. We don't even need the car. Don't need this hash either. So we should be getting one more. Why are our strings ending up the same? We're saying car hash sub IDX. Oh, car hash is indexed with the. I see. We're just actually, car hash is actually returning an empty string here, which is why all the values look the same. We do still need access to the string itself to access the correct value. Oh, in car hash. So if we use the example test cases, then I'll remove puts. So this should just be s plus t, I think. Even though we're doing 2 iterations, but. There's still time limit exceeded? S sub s dot length can be up to 5 times 10 to the 4. I guess they're looking for a version where we don't have to iterate over both strings twice. Oh, and then also the string comparison is a lot. I guess we could do this. We could do this at the same time. Now that I'm thinking about it. So if we were to take this whole function out, we'll just have SID and TID. And since they're both the same length, I think we can compress this. And then basically, we're going to check for falsehoods throughout this. And if we get all the way down here, then we can return true. But how would we compress this? They're both going to be the same length as per the problem requirements. So if we look up a value, I think we're also going to need 2 separate hashes. If we look up a value in the I think we just need to make sure that the values in the hashes are the same all the time. That way we won't need these IDs. We can skip this part. So say S car is going to be S sub IDX. T car is going to be equal to T sub IDX. Right? Car hash sub S car, or S hash sub S car is going to be equal to plus equal IDX dot 2S. We'll duplicate this for T hash and T underscore car to string. We're going to say if S hash sub S car does not equal T hash sub T car, return false. I feel like this should work. Nice. Nice. Wondering why it's so slow. That is a little disappointing. Is that a Ruby thing? It says 496. I'm barely, so this, maybe there's a faster version. Maybe you don't even need a hash. I can't see how you would do this without a hash. Basically, I think there's a way to optimize this. Basically, we're just asking if the pairs of the characters are the same. And there's got to be a better way. I mean, even I understand it, depending on how many characters we're mapping to, IDX.2S can actually get pretty big. So is there a way we can circumvent this? Because what we're storing in the hash is a string that could get pretty large depending on the... This would actually not be s plus t. In the worst case, this is s plus t squared, I think. And there's definitely a linear time solution, probably with bit stuff. There's definitely a linear time solution to this. Basically want to know that the characters have the same mappings. All occurrences of a character must be replaced with another character while preserving the order of characters. No two characters may map to the same character. I think actually it might be, I think I see what the problem is. I think this linear comparison of S hash and S car is I think it's very slow. So if we, because we're repeating a lot of the same work. For example, if we have a string that has a lot of repetition in it, and we just say, for example, for the hash A, right, we have, 0, 1, 2, and then later on in the string we find another A, dot, 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 right, and then we end up with, another A at index 45 or something. We still have to check all of this up to here, even though we already know that it's been validated. Maybe one way to speed this up would just be to not do comparisons and just do comparisons at the end. That would give us S plus T time, I think. But all this, I think all the problem is all this string concatenation. Actually, adding to the end of a string may be fine. I think if we set s hash of scar back to an empty string after the comparison, then what are we actually checking there? I think my mental model of this problem is incomplete because this definitely does not work. Even though I think in theory it should work. Zero, one, 0, 1, check this. If they're not the same. So I think a better way that actually would work is to just skip this if check every single time and just return it instead. Or I guess what I'm saying is we could have another set of variables, SID equals empty string, TID equals empty string. We add these values to S hash. We have SID plus equal, not IDX2S because we end up just counting up again. I think what we probably would want this actually wouldn't speed it up because we end up adding a bunch of these things again anyway, which we have to recalculate. I think there's a linear time solution to this, so maybe we'll try that tomorrow, but running a bit low on time, so we're going to cut for today.